Hi, this is Project 3, the Astrobee Project for Group 29. This is the design section. Our concept was for the Astro Jacket. The purpose of this robot was to create a zero-gravity robot designed for operation in orbit with the International Space Station. Some of the applications include assisting on scientific missions and with station maintenance, storing samples or experiments for long periods of time and space, and performing high accuracy space observation using an integrated telescope. Some of the additional components include 6 degrees of freedom for precise movement, a propulsion system which decouples rotational and translational motion, and multiple safety features in order to stay safe in orbit with the ISS, including blinking lights and bumpers. These are the robot subsystems and mechanisms. The propulsion system has 2 nozzles or thrusters per face, which are positioned at the midline. The orientation of these thrusters allows opposite face pairs to provide roll, pitch, and yaw mobility. The sensors and navigation include a camera on each face for environmental data collection, and temperature sensors, which allow for monitoring internal and external conditions, along with an onboard computer for all obstacle detection and any other autonomous operation. It has adaptability in the way that it has a modular design which supports many different mission configurations, including a compact, centralized storage space for experiments and science missions. This is an additional visual. It's a cross-section of the robot and includes, as you can see here, the compartments for the thrusters, the onboard computer, and you can see the bumpers along with the lid for the onboard compartment for science experiments. As you can see, this is a 3D visual. You can see the hole inside that, which is the compartment. You can see the thrusters, the 2 thrusters on multiple faces, and you can see the cameras on each of the faces and the temperature sensors.
So for the 2D dynamics part of the project, here is our 2D equations of motion of the force, the center of mass, and then the linear and angular accelerations. The main thing to note here is that the force in the y direction is always set to 0 for this part of the project because the 2 thrusters on the top and bottom of the Astro jacket are always turned off. So for the actual code itself, on the left, we see that we've defined the initial parameters such as mass and moment of inertia. And then on the right is setting up the initial conditions for the thrusters, their angles, as well as their positions. And then at the bottom, you can see how our code actually functions by using stages, which set up the position of the Astro jacket. So for example, one stage is starting to turn, or another stage is having completed a rotation. And by keeping track of these stages and figuring out when each stage applies, we're able to track the path of the Astro jacket. So here is a video of the initial 2D simulation where the first 2 thrusters are set to 90 degrees, and as you can see, that causes a spinning and rotation motion where it follows the path shown in the video.
Okay, so now using what we've learned from milestone 2, we've decided to essentially program this Astro Jacket to kind of avoid an obstacle. And so, go ahead, clicking the video. Um, we set this Astro Jacket to an initial velocity of about 2 meters per second, and at about 14 meters, you'll notice that it begins to activate the third and fourth thrusters, activating the first stage. And so essentially by detecting the obstacle about 10-15 meters ahead, it essentially knows when to slow down and then activates the thrusters to slow down, and then it uses, I believe, to every other thruster to rotate, and then it uses the corresponding thrusters to slow down the rotation. And so as you'll see, once it gets to one of the corners, it activates like either the first or third to rotate it, and then it will activate the second and fourth to slow down the rotation so that it goes to its stationary point. And the dotted line here is the ideal path that it's supposed to follow, and this is the actual path that it's following. And so here you can also see the graphs for the thrusters and when they were turned on. Notice how for the third and fourth thrusters, those have the first instance of the actual thrust, which in this case was 1,000 each time. And so that kind of corresponds to when it first actually turned on with the first stage activated.
Here are some more plots. So here you can see the x and y positions on the top, and then you can see the x and y velocities on the bottom. The main thing to note here is that the critical points are where the Astrobee is actually turning to create the turning maneuver to dodge the obstacle. On this slide, you can see the angular velocity and angular momentum on top. This is pretty similar as well. It again shows you the turning maneuver on the critical points. And then on the bottom, you can see the error graph, which compares our path to the theoretical path that we were intending to get the first time around. So here in milestone 4, you have this video here which we can play, and this shows the Astrobee now moving without dodging an obstacle. Instead, it's on a free path in the shape of a triangular figure 8, and it's powered entirely by thrust. There's no initial velocity here.
And so likewise, you can see the actual thrust plots themselves, and you can notice how two thrusters, for example, thrusters 1 and 2, are powered all the way till the halfway point of the actual dotted line, and then the back thrusters are powered on so that it essentially slows down. And so for the ideal path, it's supposed to follow this, again, the dotted line, and you can see the following plot otherwise. And likewise, we also have the X and Y positions and their velocities, with the critical points being similar to that of milestone 3. And in addition, the same thing applies for the angular velocity and the angular momentum.
So for milestone 5, which represents improvements to this design, you could transform it from 2D to 3D, meaning you would add the thrusters on the top and bottom to allow for easier vertical movement rather than turning it every single time. In a similar fashion, you could add a GPS to help with position tracking instead of relying on a camera, which would also help for collision prevention. Similarly, you could add a radar for distance tracking to also help with collision prevention. And in order to make the Astro Jacket more efficient, you can increase the speed either by using higher thrust for the thrusters or decreasing the mass or moment of inertia.
So to create a 3D simulation, we had to extrapolate the X and Y components of force, velocity, and acceleration from the first part to 3 components. We used Euler's dynamical equation to relate the moments from each thruster, of which there are now 12, with the change in angular velocity, which can then be propagated to the change in Euler angles by applying the inverse of the rotation matrix. Likewise, we went from acceleration to velocity into position using the dynamical equations in linear motion. To demonstrate the 3D functionality, we created an initial simulation where the Astrobee moves vertically, and I'll play it again more slowly. It moves vertically while also spinning in the yaw direction. So the line that represents the trajectory demonstrates that the center of mass moves in a straight line while the body itself is rotating. Now to demonstrate a change in Euler angle sequence following the familiar body 3-2-1 sequence, the opposite thrusters are fired in 6 stages, in which the turning in each orientation is both started and stopped by firing alternative thrusters, and all 3 Euler angles are changed to a non-zero value, which is demonstrated in these graphs, where the yaw changes first, then pitch, and then roll. Some potential improvements for the 3D robot design after running these simulations are that more thrusters could be added to more finely control the rotation and linear motion, and perhaps also we could use inertial rotation wheels on the inside to further decouple translation and rotation. Thank you for listening.
Yeah.